We're rolling.
Hello, today we want to look at a new topic involving integration, an application where we're looking at the area between two curves. So previously, when we first looked at integration, one of our first applications was finding the area under a curve. You may remember for a function such as this one, y equals x plus 6, we've got this linear function here, and we found the area underneath by estimating using rectangles. It forms your Riemann sum, and the limit as n goes to infinity, the number of rectangles you have, gives you that area exactly. Now, for a problem such as this, if we were finding the area between 0 and 3, this is a trapezoidal region. Calculus is not necessary, but we could use that tool. So that's a linear function. We know how to do that. We might have another function such as this one. Again, finding the area under that curve, we know what to do. We've done that before. What we want to look at today is something different, finding the area between these two curves. So one way we could approach this problem is to think about how we were first tackled the blue curve there, the function f of x equals x plus 6, or if you like the equation y equals x plus 6. So we would find the area under that. What we want to find is the area in between. So if we found the area under the blue curve, and then find the area under the orange curve and take the difference, we would have the region exactly that we want, that area between the blue curve and the orange curve. That's what we're looking at today, that type of problem. We'll look at curves that are more interesting where calculus is required, because in this case again, we would have just a trapezoidal region, and calculus is more than necessary, more than what we need to figure out that problem. So in general, we have the following. If f of x and g of x are continuous functions, with f of x greater than or equal to g of x on the interval from a to b, the area between these two curves is given by the following. Now we have a definite integral, which is not surprising. Based on our first look at finding areas under curves, we used integrals. And what we want to do is kind of build up from the example we just mentioned. We're finding the area between the curves. We find the upper or the larger function, in this case what we would call f, minus the smaller or lower function, in this case what we would call g. So the area in between is going to be definite integral over that interval of the difference of these two functions. So this is what we want to keep in mind, and this will be what we use to find the area between two curves moving forward. So with this in mind, we can try to tackle a more interesting problem such as the one we have here. Here we want to find the area of the region bounded by y equals 9x minus 3x squared. That has a graph, that quadratic function has a parabolic graph here, we see in blue. And y equals 9 minus 3x. This is a linear function whose graph we have in orange there. So we're interested in finding the area between these two curves, right in here. So we see that the blue curve, which is the parabolic graph, which is the quadratic function, is the upper function or the larger function over the interval in question. It looks to be 1, 3. To check that, we could do the following. We want to see where do these functions coincide, where do their graphs intersect. And so we set 9x minus 3x squared equal to 9 minus 3x. Getting everything onto one side of the equation, I've got 0 equals 3x squared minus 12x plus 9. Or 3 times quantity x squared minus 4x plus 3. And finally, that's 3 times x minus 1 times x minus 3. So our solutions are x equals 1, x equals 3. We suspected as much from the graph, but this just confirms it. So we know our larger function, that's going to be the quadratic function, 9x minus 3x squared, and we know our lower function, that's the linear function, 9 minus 3x. This is over the interval 1 to 3, and so the next step is to complete that integration. All right, let's start with what we know. Our upper function was y equals 9x minus 3x squared. Our lower was a linear function, y equals 9 minus 3x. And this is over the interval (1 to 3). So the area between these two curves, again, using the result that we've discussed, we want to integrate from 1 to 3 the upper function, 9x minus 3x squared, minus the lower function, 9 minus 3x. And a tip here, one thing we want to be careful with is we're subtracting this entire lower function. If we forget these parentheses, we get a different result and we get an incorrect result. So putting everything together, we have negative 9 plus 12x minus 3x squared. And from there, it's a matter of using the properties we know. We can use the power rule multiple times, and we've got negative 9x plus 6x squared minus x cubed from 1 to 3. We're careful with our bookkeeping here. Negative 9 times 3 plus 6 times 3 squared minus 3 cubed. And we subtract our evaluating at 1. We've done all the hard work now, we just need to be careful with our bookkeeping. And taking the space up here. We end up with negative 27 minus 27. We have 54 in the middle, so we end up with 0 minus negative 4. And so our total area between those two curves is 4. So we've just seen an example of how to find the area between two curves. Here are some things you can keep in mind when you're working on problems on your own. One thing to keep in mind, in the setup that we had, we must have f of x greater than or equal to g of x for all x in that interval using our setup. So the name f of x doesn't matter, g of x doesn't matter, but that relationship, that upper function, the lower function, it needs to be, that difference needs to be positive or at least non-negative. You know that from a single function, finding the area under the curve, we require that to be positive. It's the same situation here where basically the function that you would be using is f minus g. That needs to be greater than or equal to 0. What can happen is you could have a function where the curves look like this. Where we want to find the area there and there. For part of the curve, one of them is greater. For part of the curve, or for part of the interval, one of them is greater. For the other part of the interval, the other one is greater. So if that happens, you need to break it up into several parts in your integral. The second thing to keep in mind is if the bounds, so if the limits of integration are not given, we must find them. So in early problems, you might be told, find the area bounded by these two curves between x equals 1 and x equals 10, for example. For another, like the example we saw, we wanted to find the area of the region bounded by the two curves. Finding those limits of integration means setting those functions, setting those equations equal, solving for when they coincide. That gives you the points of intersection, how we found 1 and 3 in our example. So a couple things to keep in mind there. First one is very important. The second one, something to keep in mind. You might be given that information, you might not. You want to be prepared to handle that.